Finding the correct pose of a ligand in the active site is not always easy, especially for large and flexible ligands in solvent-exposed binding pockets. If we look at the chemical structure of the native ligand DHF and the drug molecules pyrimethamine, methotrexate, and pemetrexate, we see many similar substructure elements. We can take advantage of this similarity by docking using a co-crystallized ligand as a template, under the assumption that similar chemical groups will bind in a similar pose. Our template will be the co-crystallized folate ligand, and we will apply a maximum common substructure or MCS search to find pairs of matching atoms between the folate and the drugs we want to dock. Using MCS-derived restraints will cause docking to generate ligand poses that are similar to the template. Here we can see the results from known positions of the drugs overlaid on the co-crystallized folate. We see a general match with minor binding mode differences. The protein structure we'll use is 4RGC. 4RGC is a crystal structure of E. coli DHFR with a bound NADP cofactor and the oxidized form of folate, denoted as FOL. In addition to redocking the native ligand, we would like to dock 3 drugs: pyrimethamine, methotrexate, and pemetrexate. To begin, go to EnzyDocker, type 4RGC, and click Next. We select all the segments we want to include: the first protein chain, the NADP cofactor named NAP, the FOL substrate, and 2 manganese ions. Then we click Next. For most organic ligands and cofactors, we leave reading heterochain residues with the default settings. For the manganese ions, we specify the oxidation state through CSML search. We want divalent manganese, so we select the Mn2p residue. Then we click Next to generate a CHARMM-compatible PDB file. When it finishes, you should inspect the structure to ensure that it was read correctly. Just like in the previous demos, we need to set the binding site location, grid size, and grid resolution. Here, 20 angstrom should be enough, as it contains the entire ligand. In this demo, we choose option number 1 to define the binding site using residues around the ligand FOL. Since we know that aspartate 27 is important for ligand binding, we mark it as a flexible residue to account for induced fit effects. Finally, we inspect the resulting grid and click Next. The ligand bound to DHFR in the crystal structure is the native one. To dock additional ligands, we upload them through the ligand upload options and click Next. On this page, we want to adjust the protonation and oxidation state of our NADP cofactor to verify that it appears in the NADPH reduced form rather than the oxidized NADP plus form. We tick NAP to serve as a cofactor along with the manganese ions and remove them from the list of the ligands to be docked, leaving Het A, which is the folate, and the ligands we've uploaded. Click Open to edit the NADP cofactor. We adjust the charges and protonation states of the phosphate groups, the aromatic system, and the catalytic hydride. We choose the Matching Elements option to let the cofactor keep its experimental coordinates, then click Next. Then, we edit the folate ligand to its reduced form, DHF, which is the form the enzyme can reduce. Click Open to edit folate. We adjust the charges and protonation states of the carboxylate groups and the aromatic system and click Next. Click Check to ensure that CGNFF can parameterize our ligands. Since we got a green check, we can continue. We mentioned before that we want to use the experimental ligand as a reference structure to guide our docking of the drugs. Here we define Het A as the reference ligand at the bottom of the screen and click Next. Here we can inspect the protein, cofactor, and reference ligand structure and set a few docking options. We want to add 2 kinds of restraints here. The first are MCS restraints to guide the docking of the drugs. We add them by clicking Add in the Add MCS Restraints column. We only choose the drugs, not Het A, which is DHF. The restraints appear below. Any of them can be edited or removed as desired. The other kind of restraint is to guide the docking of the native ligand by the creation of 2 hydrogen bonds with aspartate 27. We show Het A, enable flexible residues, and hover with the mouse to get the relevant atom names. The ligand's N3 atom binds with the aspartate's OD2, and the ligand's N2 binds with the aspartate's OD1. We use an additional catalytic restraint between the carbon of the cofactor bearing the catalytic hydride, C19, and the carbon of the ligand that will receive it, C4. To add these 3 restraints, we make sure our restrained ligand is ligand 1 and add them. We adjust our max to be 3.0 or 3.5 angstrom, so the restraints will only apply if the atoms are at greater distances than these values. The other settings at the bottom govern the sampling conditions of all ligands, as described in the first demo. We uncheck QMMM minimization to allow faster docking. Once the docking is complete, we will inspect the poses, their RMSD and energy. Here we see a list of docked poses. We see 16 poses of the first ligand with their scoring and RMSD. The first cluster contains 5 similar poses with the lowest energy and relatively low RMSD values. In contrast, the second pose has higher energy and RMSD values. The RMSD values of the remaining ligands are with respect to the Cartesian coordinates in the mol2 files we supplied, so they are arbitrary. After downloading the project, note that the EnzyDoc results are located in the 4rgc directory, matching the PDB ID we chose, and all PDB files can be found in the results subdirectory.